Hey guys, today I'm going to be teaching you about K and Q and solubility equilibrium. So, as you guys already know, K is a ratio of equilibrium concentrations of products to reactants. And this is given to you by K equals products raised to the stoichiometric coefficient over reactants raised to the stoichiometric coefficients. But what you guys haven't learned yet is Q, and Q is a type of ratio of non-equilibrium concentrations of products to reactants. Q is basically like a snapshot of the ions in the solution, and it's given to you by products raised to the stoichiometric coefficient over reactants raised to the stoichiometric coefficients. But what the problem will give you is a solution and it tells you that it's not at equilibrium. And what Q can help you understand is whether a reaction will move forward, backward, or stay the same to reach equilibrium. And we can do this by comparing Q to K. And by doing this, it'll help you understand what the solution is doing at that given moment. Okay, so Qsp and Qsp. As I said before, Q is when the reaction is not at equilibrium. So that means the rate of the forward reaction does not equal the rate of the reverse reaction. And Ksp is when the rate of the forward and the rate of the reverse reaction are equal. So Q gives the same ratio for the equilibrium expression as K, but again, for a system that is not necessarily at equilibrium. So in terms of solubility in solutions, because this has a little subscript talking about solution indicated by SP, we can use Q and K to see how much things will dissolve, such as like a salt. Okay, so when a salt dissolves, usually the equation kind of looks the same for a lot of the problems. Usually it's a solid or a salt, which is given to you by AB, dissolves into A plus, which is also your cation, and that would be aqueous, plus B minus, which is your anion, and that would also be aqueous because these are all in solution. And then this one would be a solid because this is the salt that you're starting with. So when you write your equilibrium expression, remember that we don't include solids in it. So this would not be included in the Q or K, depending whether or not it's at equilibrium. So right now I'm going to use Q because we don't know necessarily if the system is at equilibrium or not. So you would only include these two products, which goes on the top. So this would be your Q expression. And your K expression would be the exact same thing. The only thing is K just represents if your system were to be at equilibrium. So what you can do with Q is see, since it's like a snapshot of what your solution's looking at, like at the moment, you can use Q to see whether or not your solution needs more salts or more solute to become equilibrium, or if it needs less solute to become equilibrium. So, like it says up here, if Q is less than your equilibrium constant, or so like if the concentrations are less than the concentrations in your actual equilibrium constant, that means that you won't have a precipitate because you don't have enough salt in it to form a precipitate and it's unsaturated. So which means that more ions could dissolve to make your solution be at equilibrium. But if your Qsp equals your Ksp, then that means your system is at equilibrium and that your solution is perfectly saturated. And if Qsp is more than Ksp, which means that your concentrations here are higher than if they were at equilibrium for this expression, that means a precipitate would form because you have too much salt for your solution to handle, and that means your solution becomes super saturated. Okay, so now we're going to practice using Q to predict if a precipitate will form in a reaction like this one. So this example says, predict whether precipitate will form if 200 milliliters of 0.03 molar CaCl2 is added to 200 milliliters of 0.080 molar NaOH. So here is your balanced equation. And right now, the first thing we want to see is which one is going to be the solid in this precipitate reaction, and which one is going to stay aqueous and not form a precipitate. So we'll see that NaCl is a soluble compound because Na is always soluble, and it won't form a precipitate. But however, CaOH2, it is probably going to be your solid because this one's aqueous and this one must be solid if it's like a precipitate reaction. And it is sparingly soluble with Ksp if Ksp equals 5.0 times 10 to the negative 6. So it might precipitate if the concentrations of its ions are high enough. So that's what we want to figure out. We want to figure out if this K, or not K, this Q ratio, or if your Q, because this is the ratio of all the things, you want to see if your Q is either going to be less than or greater than or equal to your K. And we're trying to see if Q is more than K to form a precipitate. So since we figured out that CaOH2 solid is the only thing that could maybe make a precipitate, we only want to focus on CaOH2 because NaCl would definitely not make the precipitate because it's soluble. So you would first write out your net ionic equation, and that would be CaOH2 solid dissolves into Ca2 plus aqueous and 2OH minus aqueous. And then you can write your Qsp expression. Remember that you do not include solids. So your Qsp would be Ca2 plus times OH minus to the second power. Don't forget about this power because of this coefficient. So once you have your Qsp expression, what I usually do is write out what we're trying to figure out. We're trying to figure out if Q is more than K, and K was given to us in the original problem that it is 5.0 times 10 to the negative 6. So we're trying to figure out if our Q expression is going to be more than K with the concentrations that it gave us originally. So since it gave us concentrations and it asked us to add two solutions together, that is also, you have to consider that it's being diluted. So in that way we use this equation. And we want to figure out if our Q, so after the solution is diluted, is going to be more than K. So you want to solve for M2. So this is going to be the equation you use. And then these M2s are going to give you these two. So you're originally given that you have 200 milliliters of 0.030 molar of CaCl2, and you're originally given 200 milliliters of 0.080 molar of NaOH. And since you're only focusing on OH and Ca here because those are the two ions that would make the precipitate, you want to figure out the M2 of CaCl2 first, so you're focusing on Ca and OH. Oops. Okay, what? I don't know why it's not circling. Okay, so Ca2 plus, that M2 concentration is going to equal M1, which is 0.030 molar, times 200 milliliters, which you had originally. And you want to divide that by the final volume that you get. And remember, this part's easy to forget for dilutions, but that your dilution is going to result in 400 milliliters of total solution. So that's what's going to be your V2. And after calculating that, it's going to be 0.015 molar of Ca2 plus. And then you're going to do the same thing for OH minus. And it's going to be 0.08 molar times 200 milliliters of 400 milliliters total at the end. That's going to give you 0, that's a decimal point, 40 milliliters of OH minus. Okay, so now what you can do is you can plug these concentrations back into your Q expression. And so that will give you 0.015 for Ca2 plus times 0.040. And then remember that you had this power. So don't forget to square that one. So your QSB, after plugging that into your calculator, it gives you 2.4 times 10 to the negative 5. And then we want to compare, remember, Q to K and see if this is true. So right now we're going to see if 2.4 times 10 to the negative 5, oh my gosh, negative 5 is more than 2, what was it? 5.0 times 10 to the negative 6. And as you can see that this clearly indicates that it is more than negative 6. So that means that since Q is more than K, the concentrations of Ca2 plus and OH minus are high enough to cause a precipitate to form. And now see that you've proved that. Your final answer is that a precipitate will form. And you're done. For this one, take a sec and try it on your own. Okay, so I wrote out the complete ionic equation just to figure out which one is going to be, or which compound is going to be the solid. And I figured that out because KBr is always soluble, since K is always soluble in solution. So CaSO4 is going to be your solid, so you want to focus on that since we're trying to figure out if a precipitate will form. And remember, that means Q is greater than K. So I wrote out the net ionic equation for CaSO4 solid, which will dissolve into Ca2 plus SO4 2 minus. I also pre-wrote out what it tells us, what we're given. And we're going to have to use a Q expression, first of all. And our Q expression is going to be Ca2 plus times SO4 2 minus. Oh. And we're going to have to do the M1 V1 equals M2 V2 equation. Use that one again. And for Ca, we're going to use that compound since it's a 1-to-1 mole ratio to the compound. Ca is to the compound, so it's going to be 250 milliliters times 0.015 molar all over the total amount of solution, which is 375 milliliters. So 375 milliliters, and that would give you 0.100 molarity. Do the same thing with SO4, so going to be 125 milliliters times, there we go, over 375. And this is for SO4 2 minus. Make sure I got it. Yeah, okay. And that would equal 0.00333 and so on. Molarity. So now you plug it back into your Q equation. Oops. You plug it back into your Q, and that's going to be Ca2 plus, which is 0.010 molarity, or molarity, times 0.00333 for SO4 2 minus. And then when you calculate that out, you get 3.3 times 10 to the negative fifth. And that is your Q. And now what you want to do finally is compare that to the K. And the K was given to us. It's 4.9 times 10 to the negative 5. So we see that K is larger than Q. So Q is less than K. So this means that a precipitate will not form because Q doesn't have as high of a concentration as K, so it is not at equilibrium, and it is no precipitate will form. And that is the end of that question. All right, so that was Q and Ksp. Hopefully you guys learned something new, and hopefully this all made sense. And if there was any weird noises, I apologize. But yeah, thank you for letting me teach you.